In this example, we are going to study the function g of s and its stability in the frequency domain. Let's start by drawing the Bode plot of g of s, and then based on the Bode plot, infer stability of the closed loop system if g of s is to be used in a unit feedback loop. Then let's try to relate g of s, the Bode plot and the Bode plot to its root locus, Nyquist, and maybe Routh Hurwitz to see how they are related. Let's start with the Bode plot. To do the Bode plot, first we need to write this expression in its standard form for Bode plot analysis, which by now we know is in the following format. We need the denominator to be written as s over omega 0 all squared plus 2 zeta s over omega 0 plus 1. And here we have a constant c. This is explained in lecture 17. So here we are going to just give the final result for this manipulation. This is very simple. We simply divide the entire denominator and the numerator by 25 and then rearrange here to have s over 5 in this part of the transfer function. So this gives g of s as 0.4 over s divided by s over 5 squared. This is the crossover frequency plus 0.02 times s over 5 plus 1. So here we have 2 zeta equals to 0.05. This is the damping ratio, 0.01. And we have the cutoff frequency at 5 radians per second. With this information, we can now start the Bode plot. How would we start the Bode plot for this? This is a bit more complicated than the previous example. Here we have a complex number in the denominator, or we can see that from the damping ratio is less than 1, so this has complex conjugate roots. And also we have a pole at the origin, so this will make the analysis a bit more complicated. In the previous examples, we started by looking at very low frequencies and determined what was affecting the Bode plot at low frequencies. That was relatively easy because it didn't have zeros or pole at the origin, which is not the case here. Here we have a gain and a pole at the origin, and that will affect the Bode plot at low frequencies. So how do we account for that? Now we need to account for the slope added at all frequencies by this 1 over s, by this pole at the origin. In addition to the pole at the origin, we have the gain. So we have these two things to account for: a constant slope coming from this pole, which is negative 20 decibels per decade, as we know, passing at 0 decibels at 1 radians per second, 20 log of 1 is 0, and the gain at 0.4, which will make the Bode plot shift up or down. So let's start by looking at the pole at the origin. The pole at the origin, we know that it will create a slope of negative 20 decibels per decade everywhere on the Bode plot, and will pass through 0 dB at 1 radians per second. So, at 1 radians per second, we would be at 0. 1 decade before that, we would be 20 decibels higher because this slope is decreasing as we increase the frequency. So if we decrease the frequency, the magnitude increases. By going back by 1 decade in frequency, the Bode plot goes up by 20 dB. So, if we only had 1 over s, the magnitude of the Bode plot at 0.1 radians per second would be 20 dB. However, this is not the only thing affecting the Bode plot. We also have at low frequencies this gain here at 0.4. So we need to account for that. So we have 20 plus 20 log of 0.4. And this is approximately 12 dB. So this is the initial value of the Bode plot at the chosen initial frequency here of 0.1 radians per second. If we go 1 decade back, then what would be the magnitude there? If we go to 0.01 radians per second, it would be 12 plus 20. Remember that at this 20 log of 0.04, this plus 20 log of 0.04 is coming from here, and it's shifting the entire Bode plot down by specifically 8 dB. Right? This is 20 log of 0.4 is negative 8 dB. Very well, so at 10 to the power of negative 1, we should start our Bode plot at 12 dB, right there. Now we can start to increase the frequency. As we increase the frequency, we always have to account now for this 1 over s, this pole at the origin. So if at 10 to the power of negative 1 we are at 12 dB, what would be the magnitude at 10 to the power of 0 at 1 radians per second? Well, the answer is here, is negative 8 dB, or 12 minus 20. If the frequency is increased by 1 decade, then the Bode plot goes down by negative 20 dB. 12 minus 20 is negative 8. Another way to see this is that at exactly 1 radians per second, the pole at the origin passes through 0. So the only thing affecting the Bode plot is the gain. 20 log of a 0.4 is negative 8. So here we should be at around negative 8 dB. And this is at 1 radians per second. Now we can keep increasing the frequency, and the Bode plot will continue to go down following this slope of negative 20 dB per decade. However, we have to stop at 5 radians per second because that's where our cutoff frequency is. It's around here at 5 radians per second. So what is the magnitude at 5 radians per second? Well, we can of course use the analytical calculation to determine that, but you can also do this based on the Bode plot without having the transfer function. By simply knowing that if here we are at negative 8 dB, what would be the magnitude at 5? Well, let's think about that. At 1, we are at negative 8 dB. And what is the magnitude at 5? What is happening between 1 radians per second and 5 radians per second? We still have this slope of negative 20 decibels per decade. Between 1 and 5, this is not a decade. The decade is 1 to 10. So if we are going to from 1 to 10, it would be easy to calculate now the magnitude at 10 radians per second. That would be negative 8 minus 20, negative 28. But you need to stop at 5 because there is a cutoff frequency there. The slope will change after 5. So from 1 to 5, we are actually half of a decade, halfway. We cannot say that the Bode plot will go down by negative 10 dB because this is not a linear scale. So we know that the slope is negative 20 decibels per decade. So starting at negative 8, we are going to move by negative 20 log of the frequency change. If we are doing a frequency change of 10, that it would be, say, going from 1 to 10, this would be 10 divided by 1, which is 10. 20 log of 10 is 20. We would be at 28. But we are stopping at 5 radians per second. So this is now 5 divided by 1. We are starting at 1 and you're going towards 5. Right? You're starting at 1 and we are going to stop at 5 radians per second. Again, if you're going by a full decade, this would be 10 and you would go down by negative 20. We are only stopping at 5. It is half of decade, but this is not a linear scale. We are going to have 8 minus 20 log of 5. So this is approximately negative 21 dB. Okay, so if we keep going here at around 5, we should be around here. I'll try to keep this as straight as possible. Let's put it right there. It's not really on scale. This should be around negative 21 dB. So we would be at 5 at 21 dB. There's a problem with this analysis though, is that once we pass 5, we have a complex pole. The complex pole is here. The damping ratio of this pole is 0.01, smaller than 0.5. This means that at the cutoff frequency, we will see that a bump that will go up and down because the damping ratio is smaller than 0.5. So the actual magnitude of the Bode plot at 5 is not negative 21 because we are now going to go up by a certain amount from negative 21 because of the damping ratio at 0.01. How much is that? Well, we saw that this would be at 5 radians per second. The pole adds negative 20 log of 2 zeta. And this is plus 33 dB. So this plus 33 dB is the bump that we'll see going up, is starting at this point here. It's starting at negative 21. So we should in fact see something that will go up by 33 dB. We are at negative 21, so negative 21 plus 33 is 12 dB. So we're actually going up to exactly where we started. So now we should see something doing that, and we come back here to the same negative 21 dB. So let me erase this part that it is. So here we should be at negative 21. This bump here, this entire length here is 33 dB. So this point right there is at 12 dB. And we are back now to where we were before, just before that bump. We are back at negative 21. Good. So now we are here at negative 21. We just crossed a crossover frequency of a complex pole. What happens? The complex pole will add negative 40 decibels to the existing slope. The current slope is negative 20 dB per decade. What is the new slope? Is negative 20 minus 40. It becomes negative 60. We are at 5 radians per second at negative 21. If you go to 50 radians per second, the Bode plot now should go down by negative 60 dB. Negative 20 from here minus negative 40 from this complex pole. So starting at negative 21 minus 60, we go down to negative 81. So around here. Because the slope now became negative 60 dB per decade. This is 60, this is 1 decade from 5 to 50. And here we are at negative 81. Very good. Now let's assume that hypothetically we want to know the magnitude at 10 to the power of 2. Based on the same principle that we did here, think about it. What would be the magnitude of the Bode plot at 10 to the power of 2? Well, based on the same principle, we are at negative 81 dB. We are going down by negative 60 decibels per decade, so negative 60 log of the jump in frequency, that is 100 divided by 50. And this would be the magnitude at 100 radians per second. Very well, now let's look at the phase. Because they have a pole at the origin, the phase at low frequencies will start at negative 90 degrees. It will stay negative 90 degrees up to the cutoff frequency at 5. When you reach 5 radians per second, then you have this complex pole. The complex pole adds negative 180 degrees to the phase. So this will go down now to negative 90 minus 180 to 70. And we will stay at that up to as the frequency tends to infinity. This is not the actual value of the phase, you need to interpolate this, but because the damping ratio is very small, this will be almost like a sudden change in the phase from negative 90 to negative 270. So you should be looking at something like this. You can check this in MATLAB, you will see that this change is very sudden. And this is because the damping ratio is very small. And will pass at negative 180 degrees, right at 5 radians per second. This is the Bode plot. Very well, this is the Bode plot for our system. Now, based on this analysis, is the system closed loop stable or unstable? If we were to use the system in a unit feedback loop, the system would be closed loop unstable. Can you see that from the Bode plot? This is easy to see from the Bode plot because if you look exactly at negative 180 degrees and you go up, we see that the magnitude is 12 decibels. In order to make the magnitude be 0 decibels, exactly, we need to add negative 20 decibels. So our gain margin is negative 12 dB. This means that, again, we need to add negative 12 dB to make the combination of negative 180 degrees and 0 decibels on the Bode plot. So this will now shift down by 12 dB, and when that happens, past that point, the system becomes closed loop stable. As it stands right now, if this system was to be used in a unit feedback loop with a gain K, this would be unstable. Another way to visualize this is to look at the Nyquist plot. When you look at the Nyquist plot, we see that we have no unstable open loop poles. So P equals to 0, and we have two encirclements of -1 as it stands right now. So we have in a closed loop system two unstable roots. This is very clear from the Bode plot because we see here that we have a magnitude of 12 dB. This magnitude being positive means that the point where the Nyquist plot intersects the negative real axis is to the left of -1, and this is exactly what we see here. Right? How did we get 12 dB here? We know that when the phase of the transfer function is -180 degrees, we are crossing the negative real axis. What is the magnitude there? Well, the magnitude is the same as here, it's 12 dB. How did we get 12 dB? Well, we did 20 log of x equals to 12. We can solve for x as 10 to the power of 12 over 20, and this is approximately 4. So we are indeed to the left of -1, and we can see from both the Bode plot and from the Nyquist plot that the system is closed loop unstable. Instead of the Nyquist plot, let's look at the root locus. Here is the root locus for the same system. We see that we have two complex poles that are very close to the imaginary axis. And for a certain value of k, we are to the right of the imaginary axis. The system is closed loop unstable with two unstable poles. If this system is put in a unit feedback loop and we consider k equals to 1, this is this representation of the Bode plot here, this is where the poles are. The poles are indeed to the right of the imaginary axis and the system is closed loop unstable. So, the question now could also be, what makes the system stable? Let's put the Nyquist plot and the Bode plot together and analyze this question. What makes the system closed loop stable? Now let's reconsider the example we had before. So here is again k, we have the function g of s, and we are treating the system this way. The root locus that I showed you earlier had k equals to 1. This Bode plot, this Nyquist plot also has k equals to 1. If now k is included and it's no longer 1, what do we get? We are going to get the magnitude of the transfer function multiplied by k. This becomes now 4 times k. And from the Nyquist plot, it is easy to see that if you want the system to be closed loop stable, 4 times k needs to be smaller than 1, so that it is to the right of -1, so k needs to be smaller than 0.25. If this condition is met, what happens? The Nyquist plot shrinks to the right and is now touching -1, so anything less than 0.5 is to the right of -1, and the Nyquist plot will show that the system has no encirclements of -1. The system is now closed loop stable. What happens to the root locus? If k is exactly 0.5, on the root locus we are here, lying on the imaginary axis. And anything less than 0.25 now makes the system closed loop stable. And from the root locus we see the same behavior again. We go from having two unstable poles to no unstable poles as we reduce k from 0.25. Now if you use this feedback loop here and have k equals to 0.25, what happens to the Bode plot? Here is the Bode plot that we just calculated, and here is the new Bode plot when you have k equals to 0.25. We are multiplying the entire transfer function by 0.25. The Bode plot shifts downwards by how much? You guessed, by -12 dB, because actually 20 log of 0.25 is approximately 12 dB, -12 dB. So by doing this, the Bode plot shifts downwards, and now at -180 degrees of phase, we are exactly at 0 decibels. The magnitude is 0 decibel, and the system now is marginally stable. If we keep decreasing k below 0.25, then we are under 0 decibels and the system is closed loop stable. So as the Bode plot shifts down, the Nyquist plot shrinks, and the poles on the root locus start to move back into the stable zone. So this is our conclusion here. To make the system closed loop stable, we need K to be less than 0.025. Should we back this up with Routh Hurwitz? Well, these analysis is pretty solid, but just for fun, let's do that. Now, just to confirm the results we just found, let's again put this function in a unit feedback loop. And now use Routh Hurwitz to assess the stability of the system, or to determine the range of stability for this system. This should match all the observations we made from Bode, Nyquist, and root-locus. What is the characteristic equation of this system for the closed loop system? The closed loop transfer function is g of s times k divided by 1 plus g of s, and the characteristic equation becomes 1 plus 10k divided by s squared plus 0.1 s plus 25 equals to 0. So this gives s to the power of 3 plus 0.1 s squared plus 25s plus 10k equals to 0. We can now do the Routh Hurwitz. We start at S3, S2, S1, and S0. For S3, we have 1, S2 0.1, 25, and 10k. This value here is 0, so this value is 10 times k, and this value, let's call that A. A is 10k minus 2.5 divided by negative 0.1. If you equate this to 0, k is 0.25. When k equals to 0.25, we have a row of zeros, and the system is marginally stable. When the system is marginally stable, the root locus has poles lying on the imaginary axis, the Nyquist plot is touching -1, the Bode plot is touching -180 and 0 dB. For k is smaller than 0.25, we have all positive numbers here. There are no sign changes. The system is closed loop stable. For k greater than 0.25, then you have a negative number. Notice that we then go from positive to positive, positive to negative, negative to positive. Two sign changes, two unstable closed loop poles, as we could see from the root locus and from Nyquist analysis. So here again, we have a comprehensive analysis of this transfer function using all tools we know to assess the closed loop stability in both temporal and frequency domain. It is very important that you are able to relate Bode to Nyquist and relate root locus and Routh Hurwitz, and also connect these two parts because they are basically doing a similar analysis using a temporal domain and using frequency domain. And if your analysis is consistent and if your analysis is right, then by using any of these methods, you should come to the same conclusion. For this particular system, the conclusion is for k is smaller than 0.25, when g of s is used in a unit feedback loop such as this one, the system becomes closed loop stable. Otherwise, for k greater than 0.25, the system is unstable.